Okay, so we're going to start talking about the distribution of sample means today. And I'm going to get another Learn Smart up there that I want you to get done before next Wednesday's class. So you'll have kind of this weekend and then the first 2 days, I guess the morning of Wednesday to get that done. Just about 10 minutes, because we're going to start talking about something called confidence intervals. That's kind of the second part of that Excel assignment that we won't be able to do yet. But I want you to kind of have a look at that as you know, before we get too deep into it, because it's going to be really important for basically what we do for the rest of this course, or the majority of the rest of this course. So I believe we left off here kind of talking about biases last class. I'm going to make a little bit of a transition back to talking about some more computational stuff, which is the distribution of sample statistics. Okay, so everything we've looked at up to this point, if we go back and think about these examples, we were looking at the population mean and the population variance, or the population standard deviation. So most of the time we don't have, right, we talked about last class, we don't have population data. All we have is sample data. So if I go back down here, scroll through all this. So if all we can see is sample data, we're never actually able to observe what the population mean is. Right? Now, we can calculate a sample mean, right? But if you think about it this way, let's say I'm thinking about the average income in the US. The average income, I don't know what it is off the top of my head, but I imagine that it's a lot lower than if I had a sample of 5 people and Jeff Bezos ends up being one of those 5 people, and I take the sample average and the average income is somewhere in the millions because he's in my sample. Well, I need to make sure then there's some things I can do to make sure that my sample mean, right, will be closer to what my population mean actually is. Last class we talked about eliminating the biases in that, but even if we do everything we can, we could still in a small sample end up with someone like a millionaire that's going to greatly influence that sample mean and make it not very be not very accurate in terms of what the population mean is. Okay, so eventually we'll get to this idea of how do we ensure that the sample mean we see is a pretty good indicator of what the population mean is. But first we need to know, well, if I look at a sample mean, they're actually going to have their own distribution. So think about it this way. If I'm looking at for the average income in the US, and I take a sample of say 20 people, I then calculate that sample mean, write that number down. I then take a random sample of another 20 people, calculate that sample mean, write that number down. Take another sample of 20 people. I keep doing that, and let's say I do it 1,000 times. Well, I would now have an Excel data set with 1,000 different sample means, and I could make a histogram out of that and look at what the distribution of those sample means is. Okay? Now, those sample means will have their own distribution. Right? If I take samples of different sizes, that distribution will look differently. Right? Think about it this way. I'll switch from income to doing height. Let's say I'm interested with the average height of, I don't know, the US, and I randomly sample someone. Right? If my samples are only of size 1, I could randomly have one person that's, I don't know, 7'2", right? I could randomly sample and see it someone's, I don't know, 4'11". Okay? So if I think about the variation I could see in my sample means, if they were only of size 1, it's pretty wide. Now, if I take a sample of 100 people, what's the likelihood I get a sample mean out of 100 people of seeing the average height of 7'2"? Almost 0, right? The probability is almost 0. If I take a larger sample, it's more likely that I'm kind of averaging out those extreme values, and I can see a much narrower range of values. So the idea is that if I take samples of different sizes, right, going from 1 to 100, that's going to impact this distribution of my sample means as well, right? It's going to kind of narrow down the values I could see, or said differently, kind of think about, it's going to make the variance smaller. Right? So if I look at, I could think about, I don't know what sample size I'm taking. I used 1 in 100, but it could be any sample size. So how, in more general, is that sample size related to the distribution of my sample means? So what we actually know is, and for now you're going to have to believe me, I'll go through a data exercise to prove this to you, but for now, just take me at my word. If I had those 1,000 different sample means that I was talking about, all of size 20, the mean of those sample means will always be whatever the underlying population mean is. Now remember, I can't see what this population mean is, but I know that the mean of my sample means will be exactly whatever that population mean is. Okay? And we'll work through some examples like if we knew what the population mean was and then we took samples, and that way we can kind of think about we know both those values. But in practice, can't really observe this usually, this population mean. But we know the mean of our sample means, right, will always be that population mean. Okay? The variance of my sample means, so I took those samples of size 20, had 1,000 different sample means. The variance of those sample means will be the variance of the original data I sampled from divided by the sample size. So this is where this idea of if I take samples of a larger size, it kind of averages out or gets rid of those extreme outlier values that I could see. So if I take a higher sample size, that would increase this denominator, which would then reduce, right? Denominator gets larger, this fraction will get smaller. So as we have a higher and higher sample size, the variance I see on my sample means goes down. So this is the equation we have. Hopefully we know what these are. Sigma squared represents the population variance of the original data we're sampling from. Sigma squared subscripted with an X bar. Well, that's just the variance of our sample means, okay? And then n, lowercase n, is our sample size. We talked about that a little bit last class even. So if I think about this sample variance, I kind of already mentioned, as the sample size goes up, this variance on my sample means gets lower. Also, if the original data I'm sampling from has a higher variance, well, that's just going to increase the variance on my sample means as well. And this kind of makes sense. If I'm sampling income data, the variance on income is much, much higher than the variance we see on height, right? And so I know that the variance of my sample means would be much lower for height there than it would be for income. Okay? Now, one thing I wanted to kind of bring up, we'll start looking at some formulas, and they might have the standard deviation of my sample means written in one of two ways. These are really the same thing, right? You kind of imagine if I'm taking the square root of something that's squared, that cancels out, so I could just rewrite that as sigma, and then divided by the square root of n. So these are both represent the standard deviation of our sample means, but really all we're doing there is whatever the variance is, just take the square root, and that gives us a standard deviation. But we can rewrite it mathematically like this, and sometimes, depending on what information is given to us, this second format is a little bit easier to deal with, okay? I just want to bring that up now because we'll see it displayed in two different ways, okay? Kind of depends on if we're given the original population standard deviation or we're given the original population variance, right? Okay, and then don't worry about this. This is just kind of something that has to be true, but in every example we'll look at, this will definitely be true, okay? So this kind of ensures our samples aren't too large. All right, so I'll work through an example with some numbers, and we'll think about what this distribution looks like. So if I had every single birth in Indiana in 2004, and I was able to, in this data set, every single birth, so I had the population data for Indiana births, right? So I look at that population data, I find the population mean, right? Average function in Excel, variance function in Excel, and we find that the average is about 3,287, and the variance is 360,000. So that's the data that we're sampling from. We then sample 36 births, right? If I were to take, I don't know, 1,000 different samples of size 36, right? So take 36 births, calculate the average birth weight, write it down. Randomly sample another 36 births, take the average birth weight, write it down. What would the mean of those 1,000 sample means be? So I took 1,000 samples of size 36. What would the mean of those sample means be, and what would the standard deviation of those sample means be? Okay. So one way to think about this is, I've got this original variable x that I'm sampling from, okay? I know that the average is 3,287, and what? The variance is 360,000. If I think about, instead, I'm looking at sample means, okay? The distribution of my sample means will still be centered around whatever that population mean is. So the mean of my sample means will just be that 3,287, because that was the original population mean of the data I sampled from. Now the variance on those sample means, we had that equation is going to be the variance of the data I sampled from divided by our sample size. And just to recall from the slides, our sample size was 36. Okay. Now I think the problem actually asks for the standard deviation, but if I have the variance, what's the only other thing I have to do to get the standard deviation? Just take the square root, right? So if I wanted the standard deviation, it'd be the square root of that guy, right? Any questions on that? This is kind of a visual way how we think about this, okay? Now I didn't really draw these to scale because if this is the variance of my original data, what's going to be true about the variance of my sample means if I take any sample that's more than 1? Well, it's the original variance divided by some number, so that's going to be smaller than the variance of the original data. So if I wanted to draw this to scale, we could actually think about, I know that this distribution of my sample means, right, is going to be kind of narrower or more peaked, right? It's going to have a lower variance than the original data I sampled from. Okay? Any questions on this before we keep moving? Let me see if there's anything here. All right. Okay, so, right, the mean of my sample means is just that original population mean of 3,287. So I know now either A or C is correct. And then the standard deviation was what? The population variance divided by my sample size, which 360,000 divided by 36 is 10,000. Take the square root of that, that'd be 100. Okay, so we should have A there, right? Now, if I had written this out the other way, right, then in my numerator, I have just the standard deviation. Well, if the population variance was 360,000, I would take the square root of that. That's my population standard deviation, which would be 600. And then I divide by the square root of my sample size, divide by the square root of 36, right? So you can do it either way. I personally, the way that I did it on the board, I think that's probably the easier way to do it is just use that variance over my sample size, then take the square root. That's usually probably the easier way to do it, okay? But this way works as well. So what if we took samples instead, exact same setup, but we took samples of size 100? Well, what's the mean of my sample means going to be? The mean of my sample means is unimpacted by the sample size that I take. So if I'm thinking about, right, what we had before, that mean of my sample means will always be the population mean. So that's going to remain the same. That's still going to be 3,287. So I know either C or A is correct here. Now, without using the formula, if I take a sample of 100 instead of 36, and I know that if I took a sample of size 36, what? The standard deviation was 100. So if I take a higher sample, what's going to happen to the standard deviation? It's going to get smaller, right? Because if we go back to the equation, sample size goes up, larger denominator is going to reduce this, right? So I know looking at these samples of size 100 that my standard deviation has to be less than the standard deviation for 36, which was 100. So I look here, my standard deviation has to be less than 100, but I already knew my mean was 3,287. So if I'm looking at A or C, I know that C has to be the correct answer. Now I could find that it was exactly 60 by plugging everything into that equation again. It's just instead of 36 here, I would have my new sample size of 100. Any questions? I'm mostly using this one to kind of get at this idea of if I take a higher sample size, we know the standard deviation will go down, or the variance will go down for my sample means, right? Okay, so here's kind of another visual. I'm going to get rid of myself for a second. A weird way to think about this is if I look kind of at the original data, right, it has whatever variance it has. I think here this says the standard deviation is 0.8. If I take a higher sample size, so now I'm looking at my sample means when I take samples of size 5, we said we know that, so we're dividing by kind of that square root of the sample size here. We know that our standard deviation of my sample means is going to get smaller. If I then take a sample size 50, it's going to get even smaller, which I kind of already mentioned. As we get a smaller and smaller standard deviation or variance, that makes our distribution more and more peaked. So why is that interesting? Let me see if I have it here. I'm gonna draw this out because I like that one picture, but I think I can do a better job. So if I think about distributions of sample means, and for now I'm drawing them out normally distributed. That'll end up being the case when we talk about something later, but for now just think about these sample means always having this normal distribution. So if I think about, I have this normal distribution, and this is for my sample means when I take samples of size 30. If I take samples of size, say 50, what I know is going to be true is, right, the variance or standard deviation is going to get smaller, which means we'll have a more peaked distribution, which means that values around that mean, because remember, the mean of my sample means is just whatever the original population mean is. So when I take higher samples, I now have higher probabilities of seeing these values right around the population mean, even if I was only to take one sample. And that's important because we usually don't take 1,000 samples and look at the distribution. We take one sample, and we hope that that sample mean is really close to my population mean. You can see here, if I take higher and higher samples, and I get this more peaked distribution, well, now I'm ensuring that the values around that population mean are more likely for me to see. So taking larger samples essentially increases the probability that my sample mean is really close or accurate about what the value for my population mean is. Okay? That's kind of the idea of why we want to take higher and higher sample sizes. So I have, a visual here where this is kind of a simulation. You can kind of see that, right? If I do samples of different sizes, n equals 1, 3, 10, and 50, well, notice when n is equal to 1, right? And this I didn't turn into probabilities. I just kept them as frequencies. Remember, we can always turn frequencies into probabilities by dividing by the number of observations. Here, the likelihood I see values right around this mean of 50 is much lower than when I took a sample of size 50. Now, the likelihood I see values around that mean of 50, much, much higher here, right? So larger samples, generally, good thing, right? We get into some, depending exactly what we're talking about. For the most part, we want to take larger samples, okay? Because we can guarantee that we will then have a higher likelihood of seeing values right around whatever that population mean is, okay? So, if we have this underlying variable x, we take a sample, and now we know the distribution of our sample means. So one thing I didn't matter, no, we didn't start last class. So one thing I said to believe in, I'm drawing this as a normal distribution. If we're sampling from a variable that is normally distributed, we know that our sample means will also be normally distributed, okay? So we talked about, we know that the mean of my sample means will be whatever the original population mean was. And the variance of my sample means will just be the original variance I sampled from, of the data I sampled from, divided by my sample size. So if I'm sampling from a normal distribution, I know the sample means will also be normally distributed. I now know the mean of my sample means, and I know the variance of my sample means. We've talked about these, okay? Well, this is great, because if I have something that's normally distributed, I can convert that into a z-score and start to find things like, okay, what's the probability that if I see a sample mean of, I don't know, what's the probability that if I were to take a sample, I would see a sample mean of 40,000 for the average income or anything below that, right? Or what's the probability I see a sample mean in between 40 and 50,000, okay? But what happens if that original variable x isn't normally distributed? Then what's going to be true about the distribution of my sample means? Well, what ends up being true, as long as we take a sample over 30, right, sample size over 30, the central limit theorem lets us know that even if the original variable you started out sampling from doesn't have a normal distribution, your sample means will be normally distributed if you can take a sample size over 30, okay? So this now is nice because now it doesn't matter. It doesn't matter if this variable is uniformly distributed. Doesn't matter if it's log normal, exponential, whatever distribution we want to think about. I know that as long as I take a sample size over 30, my sample means will always be normally distributed. They'll always have a mean that's equal to the population mean and always have a variance that's equal to the population variance over the sample size. Okay? And I'll go through a data exercise to hopefully prove this to you. I'm not going to walk through the mathematical proofs. I always think proving to yourself things with data, it makes a lot more sense. But if you want to think visually, right, it doesn't matter which of these variables we sample from. They all are not normally distributed. If I take a sample of size 2, notice, well, these are not normal distributions. If I take a sample of size 6, well, actually, one of these ends up being normal, 2 of these end up being normally distributed. The other 2 still have some skew to them. But once I get to 30, I'm going to have these really peak distributions, and I can actually guarantee, and actually I should have said, when I said greater than 3 here, I think this should be greater than or equal to. But I'm not going to try to trip you up on that. Once I get to 30, you can see these all look like normal distributions, right? Pretty peaked, but they are normal distributions. Even though the original variable that we sampled from, none of those were normally distributed, okay? So I'm going to walk through another example with some actual data. So I mentioned in the earlier example, what if I had every single birth that occurred in Indiana in 1 year? I'd have the population data for Indiana births, right? So I actually have this data set. Let me make sure that everyone's in here. Okay. And you can actually observe these different variables for every single birth that occurred. So we've got birth weight, the length of the pregnancy or gestation period, this kind of health score, APGAR score, and then whether or not the mother smoked. So this variable is just a 1 or a 0. 1 if she smoked during the pregnancy, 0 if she didn't, okay? So if I look at that population data set, I can very easily using the average and var.p function, find the, or actually not variance, sorry, I did the standard deviation here. So stdev.p, we can find the mean and the standard deviation, the population mean and population standard deviation for each one of these variables, right? We haven't taken any samples yet. This is just the original data. So we could look at the distribution for each one of these variables. We know the mean, we know the standard deviation. So if I kind of look at the distribution for birth weight, once again, it's a biological marker, ends up being one of these things that pretty normally distributed, right? This looks like a really nice normal distribution. Maybe a little bit of a skew to it on the left side, but you know, my eyes can't distinguish that this, you know, how far away this is from a normal distribution, but pretty close. Right? The length of the pregnancy, well, we have like a lot of premature births. We don't have as many births of like 11-month kind of babies. So we have kind of this long left tail or left skew distribution here for the length of the pregnancy. So the original variable doesn't start out as normally distributed. The kind of health measure, this isn't even actually truly continuous, but if we sample from it, we'll see something ends up being true. But look, if we look here, right, this is not a normal distribution. And then I didn't even put up maternal smoking, but if I had the average was 82, then if I think about what that would look like, that would actually just be, if I think about the distribution there, well, I can only see a 0 or a 1. We had that 0.82 mothers didn't smoke, and then, oh, sorry, what am I doing? Not higher. And then I had, that would make 0.18 did smoke, right? So this isn't even, I don't know, this is a very discrete example. I mean, there's only 2 possible answers. What's going to be interesting is, though, that even if we start out with a discrete variable like this, once we take the sample means, I can actually see the sample means are continuous. Because if I take a sample size 100, I can see, you know, 0.18, 0.19, I can see whatever proportion of mothers smoked. I can see any possible value in between 0 and 1, so my sample means will be continuous. Right? And we'll look at that here in just a second. I was kind of getting ahead of myself there, but so we've got these distributions. Let's say I then randomly select 100 births, okay? I then, for those 100 births, calculate the sample mean for birth weight, the sample mean for gestation and length of pregnancy, sample mean for these other 2 variables, right? I then do this 1,000 times, okay? If I do this 1,000 times, I'm gonna have 1,000 different sample means. Well, now I can look at the distribution of those sample means. I can calculate the mean of those sample means, because I actually have values there now, and I can calculate the standard deviation, okay? So what should be true is that the mean of these 1,000 sample means for each variable should be equal to whatever the original population means were, and the standard deviation of these sample means should be whatever the original standard deviation was divided by the square root of n. Well, if my n was 100, should be the original standard deviation is just divided by 10. right? Or move that decimal point. Okay? So I look here, here's my original population data. I had the means and the standard deviations calculated, and I rounded them a little bit here. If I then look at my sample means, 1,000 different sample means, when I calculated the mean, notice it's a little bit off, right? Because theoretically, I would have to take an infinite number of sample means in order for this to be true, and I'm just trying to prove this to you with 1,000. But these are very close. In fact, if I didn't round them and I left the decimals on here, you'd see they're even closer than 1, right? It's like 3,287.3 and 3,287.8, right? But this one gets rounded up, that one got rounded down. So they're very close. So the mean of my sample means is the same as the mean of the population data. Same thing true for the length of the pregnancy, maternal smoking, and for that APGAR score. Now the standard deviations should all kind of move that decimal point one place, right? We're dividing by 10, or the square root of our sample size. Our sample size is 100. Notice each one of those standard deviations of the original population data. For our sample means, the standard deviations are that divided by 100. This divided by 100, right? 2.6 becomes 0.27. 2.66 would round to 2.7. 0.38, move the decimal point one more, 0.04 if we're rounding the second decimal. So these are very, I'm just trying to use this data to prove to you those equations what I was telling you, that when we take these as sample means, as long as the sample size is over 30, which 100 definitely is, the mean of our sample means are going to be very close. Theoretically, if we could take more than 1,000 of these, we had infinite, the mean of our sample means would actually be equal to the population mean, and the standard deviation of our sample means will be equal to the original standard deviation divided by the square root of our sample size. Okay? So this is kind of nice because I had the population data, and then I could run this exercise where I sampled from that population data and calculate means of those sample means and standard deviations of those sample means. So those equations hold, but I also told you it doesn't matter what the original variables start out distributed as, right? Once I look at my sample means, they should all be normally distributed because I took samples over 30, right? That central limit theorem should hold. Sure enough, if I look at these birth weights, the sample means are very normally distributed for birth weight, right? Length of the pregnancy, also normally distributed. APGAR score, normally distributed. Maybe a little bit of a skew still kind of on these. Maternal smoking, right? I had to break this down. If I did this by, didn't create the bins as wide here, I'd see an even more kind of continuous, nice normal distribution, even for that maternal smoking variable, which remember, started out as, actually I had it drawn here. The original variable didn't have a normal distribution, but the sample means of that maternal smoking variable, we could see, did have kind of really close to a normal distribution. Right? I also want to point out here, so if we go like to the birth weight, right? Notice the values I see for birth weight, like even just the range is from 3,000-ish to 3,500. If I look at the original variable, the values I could see range from like 200 to 5,000, right? So our sample means are going to have a much lower range, or the data isn't going to have as much variation, because when we think about that standard deviation or that variance of our sample means, it's going to be lower than the original variance of the variable because we're dividing by that sample size, or standard deviation divided by the square root of the sample size, right? So when we look at the distribution of those sample means for birth weight, we have like a much tighter range of values that we can see. Right? Okay, and the same kind of thing holds for the length of the pregnancy. We see a much smaller range of values, and for this kind of APGAR score, this health measure, okay? So hopefully this kind of helped give you some more evidence to believe what I'm saying is that as long as we can take samples over size 30, we know these sample means will be normally distributed, we know their mean will be equal to the population mean, and we know that their variance will be equal to the original variance divided by the sample size. Okay? So if that's true, we can run through these steps and we can start to use that normal distribution, convert certain values for our sample mean into z-scores, and think about the probability that we see a sample mean below a certain value, the probability we see a sample mean between two values, the probability we see a sample mean above a certain value, right? And the process will really be identical to what we were doing when we had the original population data and we were turning them into z-scores. It's just now our z-score equation, right, is going to be a little bit different. And I'll show you why here in just a second. So I'm going to use the board to show you that. So if you think about our original z-score, right? You took whatever value you were interested in finding, you subtracted the mean divided by the standard deviation. Right? Well, if you know that the sample means are normally distributed, and they'll have, the mean of my sample means is just my population mean, and the variance of my sample means is the original variance divided by my sample size. Well, now when I want to convert a value for my sample mean into a z-score, it's the same thing. It's just now, instead of looking at values for the variable x, I'm going to be looking at cutoff values for my sample mean, because that's the variable I'm now interested in. Not looking at the original variable x, I'm looking at the sample mean. I'll then subtract the mean of this normally distributed variable. I know the mean of this sample mean is just the original population mean. And then down here, I'll divide by the standard deviation of whatever variable I'm looking at, but now I'm looking at the sample mean, so I'll divide by the standard deviation of my sample means, right? Or you think about here, I was also subtracting the mean of my sample means and dividing by the standard deviation, but I know that the mean of my sample means is just the population mean, and I know the standard deviation of my sample means is equal to the square root of the variance, and this is my variance, which is the original variance of the data we sampled from over my sample size. So I can substitute in here the square root of the original variance of the data I sampled from over my sample size. Right? So that's where that z-score equation for the sample means comes from. We're still doing the same thing we were doing before. It's just now I was subtracting the mean of my sample means and dividing by the standard deviation of my sample means. Right? And the reason why I tend to take a square root is because remember, the way we write the normal distribution, it's the mean and the variance. Right? So when I want to divide by the standard deviation, I had to take the square root of that. Any questions there? Are we okay with this? No questions? You sure? I want to make sure we're all kind of, this is making sense, because like I said, it's kind of a building block for a lot of what we're going to do the rest of the course. Okay? So let's work through a few examples here. And kind of this last step, this is the idea that if I wanted the probability was greater than a certain number, once I look those values up in the z-table, I might have to like subtract them from 1, or, you know. So we'll look at some different examples where we'll see that this final step changes, right? Okay, oops. So let's have this set up, right? I've got this variable that's normally distributed. I know the population means 5. I know the population variance 2,500. I take a sample of size 100. What's the probability that from that sample, I see a sample mean that's between 10 and 15? And also, I don't know why it's different versions here. This kind of cut off my equation. So let me hit enter so you can see this a little bit easier. This is my sample mean, right? X bar. So what's the probability that this sample mean I calculate from the sample of 100 is in between 10 and 15? Okay? This is the way that we want to think about this, right? So I'll go stop here. I'll kind of draw this out for you. First thing we want to think about is I had the original variable x. It was normally distributed 5, and my mean and my variance were 5 and 2,500. Right? And I got this on the glare spot for the video, so let me write this down a little bit louder. So normally distributed, the original variable was 5 and then 2,500. Okay? I know that the distribution of my sample means, right, if I take samples of size 100, the central limit theorem is met. So I know my sample means will be normally distributed. The mean will be whatever the original mean of my variable I sampled from was, or the population mean. And my variance will be the original variance, but divided by that sample size of 100 that I took. Okay? So I can now think about the distribution of my sample means will be normally distributed around that mean of 5, and then the variance of my sample means will be what? I think this is what, 25? Right? And I want to know what's the probability I see a sample mean in between 10 and 15. Okay? So what do I need to do? I need to convert these into z-scores. Right? Once I convert those into z-scores, I can find the probability to the left of each one of those z-scores. And then my final step would be, and I'll kind of give you a second if you're kind of writing this down to write this down. I'm going to draw up, I'm going to erase this. So is everyone okay with me getting rid of this? They're fine. That was the original thing. What? And then there's a dot here because I hit enter so that we could see that it's clearly the X bar. Yeah. So that's what we want to find. Right? So, and usually I would draw this underneath, but we can draw it above, it's fine. Anytime we have a normally distributed variable, we can map those out onto z-scores, right? So, I want to find the z-score for 10, the z-score for 1, sorry, not the z-score for 1, the z-score for 15, right? I could then look up this z-score in the table. It would give me this area. If I look this z-score up in the table, it gives me this area. If I subtract the smaller from the larger one, I'm just left with what I originally wanted. Okay? So how do I turn these values into z-scores? Okay? Well, the equation we had for the z-score was take whatever cutoff value I'm interested in, so we'll do 10 first. Subtract the mean of your sample means, which is 5. Divide by the standard deviation of your sample means. Now, before we had the variance was 25. So the standard deviation would just be the square root of that, or 5. Right? So I divide by 5. That was my standard deviation for my sample means. This is equal to a z-score of 1. Okay? So I know the first z-score I want to find the area to the left of is 1. Now, the second one, let's think about this. I gave you some easy numbers. How far away is 15 from the mean? 10 away. What's my standard deviation for these sample means? 5. So how many standard deviations away is that? 2, which is, that's the definition of my z-score. The number of standard deviations away, so 2. Right? So I'll look up that z-score of 1, find the area to the left, look up the z-score of 2, find the area to the left, subtract the smaller from the larger one, and I'm done. So once we convert these to z-scores, it looks exactly like what we were doing before, right? It's just we have a slightly different equation to find our z-score because we're using, and I did these, I kind of computed, I computed these. What we could have done, if I didn't find the standard deviation of my sample mean first, the original equation would actually be something like take 10, subtract the mean, divide by the square root of 2,500 over 1,000. I just, the way I did it, I think is a little easier if we remember that what's here in the denominator just represents the standard deviation of my sample means. Because then I can calculate that first, and then I just plug it in. It's just like what we were doing before. But if I didn't want to do that intermediate step, I wanted to do it all kind of in one equation, I could have plugged in the equation that I know represents the standard deviation of my sample means. Okay? All right, so hopefully, this is kind of old hat at this point. If we turn these into z-scores, I have a picture here to kind of go with this, right? This actually looks like an example we did earlier this week. I can find the area to the left of a z-score of 1, subtract that from the area to the left of a z-score of 2, and what I'll be left with there, right, this would cancel it out, and I'm just left with what's in between. So if I look up that z-score of 1 in the table, just to kind of show you how I got those values, looking up a z-score of 1, well, that's just 1.00, so I scroll down here, 1.00. The area to the left, or the probability I saw a z-score of 1 or lower, is 0.8413. And if I look up a z-score of 2, 2.00. The probability I saw a z-score of 2 or anything below that is 0.9772. Okay? So really what this is telling me is the probability I saw the sample mean take on a value between 10 and 15, well, that's 1 and 2 standard deviations above the mean. So the probability I see something in between 1 and 2 standard deviations above the mean is, all right, grab those values from the table, we subtract the smaller from the larger, and the probability is about 0.1359. Now this slide, we did an earlier example this week, and everything looked exactly the same, except we weren't using the distribution of our sample means. We were just looking at an original variable. I kept the values the same, but I kind of did that to show you that once we convert this, whatever cutoff value for the sample means we're interested in, once I convert it into z-scores, everything looks exactly the same. I've added nothing new in terms of the process or the procedure. It's really just this first kind of step. I guess we add in, we have to make sure we have a sample size over 30. And then that second step of when we convert these to z-scores, it's going to be, we have a few more moving parts now. Now we have kind of this sample size in there. Right? Any questions on this one before we keep moving? Yeah, okay, good. All right, so let's do one more. So let's say I've got that gestation weeks or the length of the pregnancy. I've got a population mean of 39, population variance of 9. I sample 81 infants. What's the probability that I see a sample mean value for these 81 infants being over 39.5? Right? Well, right away, let's just stop and draw this out. And a lot of times, if it's multiple choice, we can rule a lot of things out, right? So I'll reference some of those values. So if you have the slides pulled up, you can kind of see that. If not, I'll go back to the slides, but I'm just going to be grabbing the values that we just read from that example. So I want to first start out thinking about, I'm looking at the distribution of sample means. I took sample of size 81 births, so my central limit theorem is met, definitely over 30. So I know my sample means will be normally distributed. I know that my sample means will have a mean, the mean of my sample means will be whatever the population mean was from the data that I sampled from. Now, if I go back to the slides, that was told to me to be 39, okay? So this is 39. I want to know what's the probability I see. I believe it was, I need to give myself a little more room here, 39.5 or greater. Right? So what do I know that probability has to be less than? 0.5. Because the area to the right of the mean is 0.5. We're dealing with a normal distribution still. So I know this area has to be less than 0.5. So when I look at those possible answers, right away I can rule out B and C, right? Now this is where it gets a little tricky. It's kind of hard to envision. I mean, even though 39.5 is really close to the mean, you might start out and you might say, well then the area to the right of that value should be close to 0.5. Well, hold on. It's close in value, but if my standard deviation was 0.1, being 0.5 away from the mean would be 5 standard deviations away. So we can't just look at the difference between the value and the mean. We need to think about, well, the standard deviation matters as well. So what would be the standard deviation of my sample means? Well, that should be the square root of whatever the variance of the original data we sampled from was, which I think was it 9, right? Divided by my sample size. So this is what, 1/9. If I take the square root of that, my standard deviation is actually only 1/3. Right? So how many standard deviations away from the mean is that value of 39.5? Well, it's actually like, what, definitely more than 1, not quite 2 standard deviations away. So when I think about what the probability should be, well, it might not be a value close to 0.5. So if I just were to guess and say 0.4 originally without first thinking about what the standard deviation was, that's not going to work. Now it's okay, you don't have to, like I'm not saying you should use all this to like guess which one. We can actually compute it and find what the exact value is, but when we're just thinking about evaluating the like credibility of the possible answers, we're starting to think here, well, we're actually pretty far away from that mean, right? You know, 1/3 is 0.333, so I mean, I'm like at least 1.5-ish standard deviations away. Okay? So what we'll do is we'll convert this cutoff value we're interested in into a z-score. We want the area to the right. When we look up this z-score, we can look it up in the table, find the area to the left. We would then subtract that from 1, and we'll have our answer, right? So how do I find this z-score? Okay. Well, I'm going to write this up here so I can get myself a marker. So we originally had, all right, we found that standard deviation. So my z-score for these sample means will be take the cutoff value I'm interested in for the sample mean of 39.5, subtract the mean of my sample means, which is 39, and then divide by the standard deviation for my sample means, which was 1/3. Right? Now, instead of doing this, what I could have done is, what I actually had the equation in here was like the square root of whatever the population variance of the sample size was. So instead of first finding the standard deviation, then plugging that into the denominator, I could have just written in this equation, which is the population variance was 9, my sample size was 81. Either way I do it, I'll get the same answer, right? And I think that should be 1.5, right, if I put that into my calculator. So I get this z-score of 1.5. I then look that up in my table. So 1.50, right? The second decimal point will be 0. So 1.50, 0.9332. Right? Well, if I look up and find the area to the left, right, of 1.5 is 0.9332. Remember, I originally wanted the area to the right. So my final step there is I need to subtract this from 1, which would then give me, right, the area to the right there, that light blue area. Okay? So 1 minus that 0.9332, and I find the area to the right of a z-score of 1.5, or the area to the right of that sample mean value of 39.5 would be about, what, 6.7%? So you can kind of see here, this is nice because if we take samples that are a high sample size, it reduced my variance quite a bit. And so now I know the probability that I see values that aren't even that far away from my population mean. Well, now I know that the probability of seeing values that aren't even that far away, if I take high sample sizes, I can reduce that to what? This was what? 0.0668? So I'm kind of guaranteeing that I see sample means that are within 0.5 of my population mean, which is good, because now I have a sample mean that's really close to my population mean. But the only reason why that happened was because I reduced that standard deviation of my sample means by taking a high sample size, right? 81. Okay. Any questions on that before we kind of end things for the day? I think we're about out of time here. So, okay. Let's check the chat. So I'll get that LearnSmart up there, get that done before class starts next Wednesday. Next week, we'll just keep talking more about distributions of sample means. We'll also start to think about sample proportions. And eventually, we're going to get to, I think, either next Wednesday or Friday, we'll start talking about confidence intervals, okay? And so that's what that LearnSmart will be about. It's about confidence intervals, kind of getting you primed for that discussion, okay? All right. Have a good weekend, and I will see you guys on Monday.